All right, back to where we left off here. Sorry about that. This will be a part 1 and part 2's video series. Oh, let me get my lock on here. We've got a meeting starting in 10 minutes, so I gotta wrap this video up. Anyhow, torque is force times radius. So how we deal with this problem, let's kind of start back over here for this video. So now we're gonna deal with a pulley that has mass and it must have friction. Like I said, all the problems we've done, if we said there was no friction, the rope could not possibly turn that pulley. In fact, the friction of the rope on the pulley is what causes the torque to rotate it. If we were to zoom in here, the force of the rope on the pulley, tangent to the pulley, so this force right here, ooh, a red marker, I just ruined it by writing in black, but that's okay. That force is rotating the pulley, just like my fingers rotating this blue tape, right? This one is trying to pull it this way, though. It's not helping. It's like trying to hold it back almost, right? So it's resisting the pulling motion. All right, so what we end up doing here is not only do we make a force diagram for each object, but we also make these are free body diagrams. This is where we have to be careful how we say this. These are free body diagrams. I'm going to make a force diagram for the pulley. Force diagram is when you draw the forces at their point of application. So that's FT1, and this is FT2. Now, some things change here. This FT acting on this block is FT2. This FT is FT1. These forces are no longer the same. The force of tension on either side of the pulley cannot be the same. If it was the same, the pulley wouldn't turn. There must be an unbalanced force on either side of the pulley to get the pulley to turn. So, a little bit different now, all right? We actually end up with 3 equations here. And my whiteboard is going to prove to be maybe a little bit too small for this. So let's go through here. So let's see these 3 equations. All right. We are going to have over here, I'm going to have to write a little bit smaller. I'm going to leave my coordinate system positive down here, positive down here. But now what about the coordinate system for this? Well, it's rotational direction, right? This is going to have an alpha. Rotating. It's going to have an angular acceleration, alpha. And remember that this tangential acceleration is r alpha. And that A, the magnitude of that A, the tangential acceleration of this pulley rotating, is the same as these 2 A's, right? The motion of this pulley, the speed of the rotation of the pulley at any time is equal to the rate at which the string is going up and down. So that A equals that A equals that A equals this A that I erased. So that's important here. So let's write Newton's second law equations. We're actually going to end up with 3 Newton's second law equations now. All right. For the 5 kilogram mass, we have 50 newtons. All right. Minus FT2 equals 5 kilograms times A. For this one, we're going to have 100 newtons. Oops, I did that backwards. My bad. FT2 minus 50 newtons. This one here, we're going to have 100 newtons minus FT1 equals 10 kilograms times A. Now this one here, all right, maybe I should just move it up a little bit, but I'll try to squeeze it in down here. For this one here, we have to do torque net equals I alpha. Torque net equals I alpha. So what does that look like? All right, so torque net, I have this force trying to rotate it, what I'm calling the positive rotational direction. I know, yes, clockwise, counterclockwise, clockwise usually negative, Counterclockwise is usually positive. However, it's a coordinate system, so you can set it any way you want. I'm going to make this way the positive direction. All right, so ft1 times the radius of this object, again we call this a rigid body, it's a pulley, times the radius of that pulley, and then we get capital R. We usually make the radius of these physical objects a capital R, the mass a capital M. It's just the way we do it. Minus ft2 times capital R. Now why am I multiplying by R? Because that's the torque due to this force. The force times the radius. I apply a force to something, and the farther away from that rotational axis, the bigger the torque. Remember from the last worksheet. So there it is. The ft1 torque is trying to pull it down. Torque 2 is trying to pull it down this way, opposite directions. And that's got to equal the I alpha for the pulley. Now, got to tie this all together. I of a pulley. I didn't tell you that, but typically we say the I of a pulley is capital, 1/2 of capital MR squared, a pulley. We usually treat it like a solid disc. All right, so put it all together. Get rid of I alpha here. I'm going to write 1/2 capital MR squared times alpha, right? But alpha we're going to write in terms of A, because I want to eliminate unknowns. So alpha now is going to go as A over R. I'm just going to solve for alpha over here. This R is the radius of the pulley, so I'm going to make it capital R. All right, so we see something kind of cool happen. Bam, bam, cancels. Bam, 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 cancels. And look what I get. I get ft1 minus ft2 equals 1/2 capital MA. All right, capital MA. So now I've got 1, 2, 3 equations, and I have ft1 and ft2 unknown. Now I have to go through and do the algebra, so to speak. All right, now I'm gonna pause this for now. I have to go into this school meeting, and I will come back and do this for you later. Thanks.